Okay, in this talk, I'm gonna talk about our work in about correlated insulating ground state of the magic angle graphene, and this is based on these two papers, mainly the second one. Here are my collaborators from Berkeley and Harvard. We have Nick, Shubayo, Mike Zalatel, Aslam, Zhongyong, and Ashwin, and also me, of course. So again, let me briefly tell you what is happening in this twisted bilayer graphene system. So we consider two graphene sheets and relatively twist them by a small angle. By this twisting, the original translation symmetry in monolayer graphene is largely broken to this large-scale Moiré translation symmetry with very large unit cells. And as a result, the monolayer Brillouin zone got folded into this tiny Moiré Brillouin zone. And since the twist angle is small, the two valleys of the graphene are still decoupled in this limit. Even including the interaction effect, there is a approximate value U1 symmetry, which we will assume throughout this talk. From some single particle theory of this system, it was predicted that if you tune the twist angle to some particular magic angle, there are two very flat bands appearing per spin valley near the charge neutrality points, and therefore effect of strong electron interactions can be expected in these systems. And indeed, experimentally, people have found correlated insulators at various integer fillings, including the charge neutrality point where the single particle theory predicts the direct dispersion. In this talk, we will be mostly focusing on charge neutrality point and half filling, which means the lower flat band is half filled for each spin valley flavor. The goal of the work is to understand the nature of these correlated insulators. There are also nearby superconductivity domes, but this is not the focus of this talk. Okay, before going to our results, I need to briefly reveal the single particle theory of this system. Instead of writing down the Hamiltonian, I would just say this theory, the single particle theory for the system, is controlled by two parameters characterizing the interlayer hopping. One is one we call W0, which is the intra-sublattice hopping, and the other is W1, which is the inter-sublattice hopping. Both from both are hoppings between the two layers. And if you consider rigid, if you suppose the graphene lattice to be rigid, then W0 is equal to W1. But in actual materials, due to relaxation effect, W0 is got reduced a little bit. And a particularly interesting limit to consider is a chiral limit introduced in this work, where we completely switch off the intra-sublattice hopping. And in this limit, the system has an enhanced chiral symmetry, meaning that the sublattice sigma z operator anti-commute with a single particle Hamiltonian. And as a result, one can actually find a completely sublattice polarized basis for the two flat bands per spin valley, and therefore we can label the wave functions in these two flat bands by valley, sublattice, and spin. And we'll use tau and sigma as the Pauli matrices acting on the valley and sublattice degrees of freedom, and the Chen number for these bands are given by sigma z tau z. Okay. In this work, we did both numerical and analytic Hartree-Fock calculations, including the realistic Coulomb interaction, and we consistently found a robust ground state for the graphene system. So let me now tell you our result. For simplicity, we'll always ignore spin, ignore the spin flavor, which means we either consider a spin singlet state at charge neutrality or a spin polarized state at half filling. And in Hartree-Fock calculation, all the correlated insulators are just a bunch of symmetry breaking states, spontaneous symmetry breaking states. So let's first reveal what are the symmetries of the system. Apart from the charge U1, value U1 symmetries, there are also some discrete symmetries in this system, including this is a spinless time reversal symmetry and C2, C3 lattice rotation symmetries. And we will characterize the possible Slater determinant states from the Hartree-Fock calculation by this equal time momentum space correlation function, which is actually the projector onto the field bands. We can write this matrix P as 1/2 times 1 plus Q, and this Q matrix takes +1 in the field bands and -1 on the unoccupied bands. So it's really like the Dirac mass term for the possible orders. What we found both numerically and analytically is that the ground state is very likely to be the following, which we call Kramer's intervalley coherent state, whose Dirac mass matrix is given by, takes this form in the Cairo limit. This order, this state breaks the spinless time reversal symmetry, but it actually symmetric and another Kramer's time reversal symmetry, which is a combination of the ordinary time reversal and a pi valley rotation. And this symmetry, this time reversal symmetry squares to -1 on single particle states. Therefore, it's like a spinfold time reversal. And it's interesting to note that due to this new spinfold time reversal symmetry and the presence of charge U1 symmetry, this Kramer's IVC state has a Z2 topology, just like the topological insulator. But it's actually tricky to look for edge states on an open system because this Kramer's time reversal involves a valley U1 valley pi rotation, which doesn't have a on-site action at the graphene scale. It's somewhat like a crystalline symmetry. It's unfortunate that this KIVC state doesn't have any sharp signature at the Moiré scale, but it does have some signature at the graphene scale. And in fact, there are, if you compute the currents flowing on the links, there's a non-zero circulating currents flowing around there. And the basic pattern is given by, is shown in this picture. In this picture, we use this double arrow to denote twice the current compared to the single arrow. And with this current pattern, we can define some scalar magnetization associated to each plaquettes, and these magnetization scalars form a periodic picture which triples the graphene unit cells. And on the Moiré scale, this magnetization looks like this, where we already we did a continuous interpolation when plotting this figure. Okay, let me now give you some analytical arguments about why these KIVC states are favored energetically. We write the effective Hamiltonian as we can write the effective Hamiltonian as an unnormal order density term plus some fermion bilinear terms, and this term is actually the highest energy scale which we wanna satisfy, in this Hamiltonian, the density operators depends on the wave function of the flat band through the form factor lambda, which takes this simple form in the Cairo limit. So if we just think about this first term, we ignore all the other terms and also consider the Cairo limit with this simple form factor, we know that the ground state must be annihilated by this density fluctuation delta rho, which gave us this following condition on the Dirac mass terms. If we include for a realistic model, we also need to include other perturbations, namely some dispersion terms in the bilinear in this bilinear part of the Hamiltonian, and also there will be additional terms contributing to the form factor, and these will give us two additional constraints on the Dirac mass terms, but they are of a lower energy scale compared to the first one. And here we list many possible orders that we can, symmetry breaking orders we can consider in this system, including the valley polarized state, and these two valley hot and quantum Hall states are C2T breaking states, and also several intervalley coherent orders breaking the value one symmetry. And we see that this KIVC state is actually the only possible mass term which satisfy all these three energy constraints. And indeed, numerically, we found this is a robust ground state. This is a ground state which is robust to tuning up many parameters of the system. And in the end, I also want to introduce another solution to the Hartree-Fock equations, which is C3 breaking semimetals, preserving both U1 valley and the C2T symmetry. A typical band structure is given in this picture. These solutions are guaranteed to be gapless due to the presence of C2T symmetry and some topological reason. And therefore, these are semimetals. These solutions are not energetically as good as the KIVC solution, but these are important because we found that if you explicitly introduce some string, some C3 breaking terms in your Hamiltonian, then many insulating states, including the KIVC solution, has a very large C3 breaking susceptibility to this string, and they all develop very large components of C3 breaking semimetals. And for example, here I plot the gap of the KIVC solution with respect to the string introduced in the system, measured in some unit. And you see that as we increase the string, the gap of the KIVC solution, the gap of the KIVC state decreases, and the band structure actually got more and more similar to this semi-metallic form. This may explain some experimentally observed nematicity in some samples. Okay, now let me summarize. In this work, we propose a possible ground state for the bilayer graphene at both charge neutrality and half filling, which is the KIVC solution given by this Dirac mass term, which has a new time reversal symmetry satisfying t prime square equals to -1. And also we propose that if you introduce some small string in the sample, there will be large C3 breaking components developed in these insulators. So experimentally there can be very strong C3 breaking signature. Okay, that's all I want to say. Thank you for listening.
So what values of mu are you referring to here?
Nu is either 0 or -2. -2 means you half fill the lowest band. Yeah.
And is this, so the STM experiment seems to show some symmetry breaking at all integer nu. Is this, you're saying that is this consistent with the STM experiment?
You mean the C3 breaking or other symmetry?
No, this is the Weizmann Israeli experiment,
Sorry, what symmetry breaking you mean?
There's a paper on the archive as STM data claiming that there are Dirac cones and various valley polarization at every integer nu.
If it's valley polarization, it's probably not the same as what we are saying here. Yeah. So
my other question is, does the STM data consistent with this also?
I'm actually not familiar with that paper. Yeah, but for half filling.
I can say something about that.
Okay.
STM, at least the one that's online, they don't see gaps.
Yeah.
That's consistent with the semi-metallic state, with flavors being polarized in sequence.
So this KIVC state is semi-metallic?
No, KIVC is fully gapped.
Oh, I see.
So there are two states over here, one is semi-metallic, one is gapped.
Okay.
It would be consistent with the semi-metallic state with some, the four flavors is sequentially polarized. KIVC is sort of, you also have that aspect, you have that polarization, but seems to be more stable at even integer filling, so 0 and 2, 0 and plus minus 2. It's not that good a solution at the order fillings.
Hi.
So is that figure supposed to represent the KIVC phase or the?
This one is a current for the KIVC solution. This left figure is supposed to be the currents pattern for the KIVC solution, but this one is a semi-metallic solution, which is another gapless solution.
Okay, because that one seems to have C3 symmetry. The one on the left has.
Yeah. The KIVC solution preserves C3 symmetry. That's another solution.
That's another one. Okay,
Yeah.
sorry, it wasn't labeled.
Sorry about this.
I thought it was supposed to be the C.
Yeah, that's a bad alignment.